So today we have Fred Sigworth coming from Yale University. He is going to tell us a little bit more about foundational math. Take it away, Fred.
Okay, thank you. Yeah, it's a real treat to be here, and this is the first time I've been here in person in a while, so it's a special treat because of that. I'm going to start with a review of complex numbers because I'm going to be using complex numbers, and I'm sure you all have heard of them, but this will be quick. And then the focus of this first lecture is the contrast transfer function. And that turns out to be absolutely the key for any high-resolution electron microscopy, and it's embedded in all of the reconstruction algorithms and so on. So I'm going to talk quite a bit about that. So complex numbers, why do it? Well, the equations are simpler, and that's a big enough reason that everyone has adopted them for Fourier transforms. So of course, complex numbers are based on having an imaginary unit that we call I, and then a complex number has a real part and an imaginary part. You can do arithmetic, so you can add, multiply, you can pick out the real part, the imaginary part. You can do something called the conjugate, which is kind of like a time reversal in quantum mechanics. And then there is a very important function that I want to talk about, which is the exponential function. So the exponential function e to the x, so you remember, is this transcendental number, and e to the x is given by an infinite series. And a very important approximation that I'm going to be using here is just taking the first order approximation that says that e to the x is approximately equal to 1 plus x if x is really small. Now, the other thing is that there's not just e to the x, but then there's e to the I something, e to the I theta. And this is a very special function that is equal to, the real part is cosine and the imaginary part is sine. And so here's a cosine function. It's 1 when the angle is 0, and then it oscillates like that. And then here is sine. It's 0 when the angle is 0, and so it oscillates in a different way, displaced by 90 degrees or quarter of a wave. And here's a representation of what e to the I theta might look like if we think about plotting the imaginary part versus the real part. It's a circle, but if we then plot it as a function of the angle theta, you can see that it's actually a helix. And so here we are viewing it where we can see the imaginary part, which is this sine function. And then if we rotate it and look at the real part, it looks like this sine function. So this cosine function. So it's a helix. The magnitude stays all the same at 1, but we say the phase changes. This theta is a phase angle, and so it takes on these complex values. So before I told you, well, we can do arithmetic with this, but we can also do arithmetic with this. This is another representation of a complex number. We say that this is a magnitude, and this is the phase term, and so we can say that this point is a plus bi in the one system, or a magnitude r and an angle theta. Okay, so that's all that, and I hope that you will interrupt me because I would much rather answer questions than tell you what I planned. Okay, so what about the phase contrast in the electron microscope? So the whole reason we can see anything in our cryo-EM specimens is that Incident electrons, when they pass near an atom, they pick up some of the positive potential at an atomic nucleus, and that positive potential changes the wavelength very slightly so that this so-called elastically scattered wave, that is an electron that has not lost any energy, has its phase shifted by something like a milliradian, just a little tiny amount of phase shift. And that's what we're going to pick up to make contrast from. Now, one of the remaining technological scandals in cryo-EM is that we have a terrible way to get contrast, which is to throw the microscope out of focus. So here's a simulation. There's this Trip V1, my favorite object for showing these things, and this is a calculation of its image, and with zero defocus you can barely see a little bit there. That little bit that you can see is actually thanks to spherical aberration in the microscope objective lens. But then as we start changing the defocus, we get more and more signal. We can see more of what I would call the low frequency components, but we also get more and more of this delocalization. You can say way out here, these are fringes, which are actually carrying high resolution information. And by image processing, we can put those fringes back together and get a good image, as I'll show you later. But in the end, you only get about half as much contrast as theoretically possible. A phase plate allows you to get all of that contrast, and that's why phase plates are really exciting, but not yet available to us mortals. Now, I'm going to use a different kind of target specimen, which is going to be a little grating. So you can imagine here's this is a grating with a 5 angstrom spacing. So imagine, beta sheet. Now let's look at what happens when we start to defocus it. So you can see that as we increase the amount of defocus, we see some signal, and then the signal disappears again, and then the signal reappears again, and actually you can't see it, but the contrast is reversed. And then if we go and do even more defocusing, you can see that not only is the central part alternating in no signal and signal, but now we've defocused so much that we're seeing the dispersion. We're seeing we're seeing these so-called side bands moving farther and farther from the center of the object. So I'm going to look at how this contrast comes about when you defocus. And the basic idea is, well, a simple way to understand it is that a grating like this produces diffracted electron waves, and those diffracted electron waves interfere. And the reason I'm talking about gratings is that in the next part of this lecture, I'm going to talk about Fourier transforms. With Fourier transforms, you can prove that if you know the response of your optical system to gratings of various, various frequency and various orientations, then you can, with gratings, you can build up any kind of image. And so if we know what happens to a grating, we will then know what happens to any kind of image. So electron waves have very short wavelengths. Our favorite 300 kV microscopes, the electron waves is about 20 picometers, and the electrons are going through the column close to the speed of light. And at the kind of doses that we use, there's one electron in the column at a time. So that electron wave is interfering with itself as it goes through the microscope. So we say with quantum mechanics that it has a wave function, and this wave function is again one of these complex exponentials, e to the I k z. So z is the z coordinate increasing downward, and K is this propagation constant, and so K is the right value such that this thing changes its phase every wavelength, every 20 picometers. Okay, so we're going to insert a phase shifting object, a grating, to perturb my wave. And so you can see, if you look carefully at the little perturbations of the wave fronts below this object. So I'm going to say that this grating is a variable phase as a function of x, and the grating periodicity is going to be 5 angstroms, and it's a very small perturbation of phase. And then we can say that, well, right after we have passed through the specimen, right here at z equals 0, the wave function is just going to be e to the I phase shift in the object, which is e to the I epsilon, which is the amplitude times phi of x, which is this grating function. Okay, now here's where I'm going to use that approximation of e to the x. So this is the function just below the specimen, and then if we use this approximation, we can say that this complex exponential can be approximated by this thing. It's 1 plus all of the variable phase part, and this variable phase part, it has I multiplying it. So this is an imaginary part of that wave function. Now there are 2 terms here, and these have physical meaning. So this term 1 says, after the wave has passed through the specimen, there's still the original undiffracted wave still propagating through, and this approximation actually gives it the same magnitude as it was before. That's why it's an approximation, but it's close. And then there's this imaginary part, and it turns out that this can be represented as 2 diffracted waves. And so we can say that the full wave function is this original incident wave plus these 2 diffracted waves. Okay, so if we now look at look from the side at the magnitude of waves below the specimen, here's what we see as we move farther away from the specimen. We start out, there's no contrast here, and then there is contrast, and then there's no contrast here, and then there's contrast. I'll play a little movie again. So you can see up here is the contrast disappearing and reappearing, and actually the amount of contrast follows this sinusoidal function. So there's no contrast there, and that's because right there at the specimen we have 1 plus this imaginary part, and it turns out that the imaginary part doesn't really do anything to the magnitude or the intensity. The intensity only changes when we get somewhere down here where that imaginary part has now changed to become a real part, and so now it's adding and subtracting from the real part of the incident wave. I'll tell you more about that in a minute. So why do we get diffracted waves? Well, this is just the standard diffraction that says that if you have a periodicity in a specimen, let's say, then that launches a new wave at an angle theta, and the theta is this number wavelength divided by the grating spacing. And in our case, this is a really small number. This is 0.02 angstroms divided by, in this case, 5 angstroms. So this theta is a really small angle. And there are two of these diffracted waves, one there and one there. My computer is changing slides more easily than I can. Okay, so we have these 2 diffracted waves, and they travel at these very small angles compared to the undiffracted wave. And so if we think about some point below the specimen, let's suppose that we focus the objective lens 100 nanometers below the specimen. So then what we are picking up is the original undiffracted wave plus these 2 diffracted waves coming in from slightly different places in the specimen. And, and that's what we see there. Now the diffracted waves, because they're going at an angle, the path length is slightly longer, and we can calculate the difference in path length. It's this distance, 100 nanometers divided by cosine theta minus 100 nanometers, and this quantity is looks like this, z times lambda squared over 2d squared. So this path length difference, in this case 100 nanometers, and the other parameters, I told you this difference in path length is only about half a wavelength. So here we are 100 nanometers below the specimen, you know, the 1,000 angstroms, and so 20,000 wavelengths below the specimen, but the phase shift due to this tiny angle is only like half a wavelength. So where the diffracted waves have the right phase, we have contrast. So I'm going to start representing complex numbers this way. So this is like the amplitude and phase diagram, but here I have this little color wheel. Imaginary numbers wind up on this axis, blue and yellow, and real numbers wind up on this axis, red and green. And so what I'm going to do is I take this, which is the actual calculation, and you can't see it, but there you can see that there is actually an electron wave there if you greatly magnify this view. But we're just seeing the magnitude of the electron waves, and we can see no contrast, contrast, no contrast. And I want to think about how this comes about. Well, the first thing I do is I get rid of the oscillation. So I just take the wave function and I undo that e to the ikz, so that the incident wave just looks like 1. It's red because it's a real number. And then the other thing I can do is I can take what's left over and subtract 1 from it. So in that case, what I have is the incident wave, which is 1, and I'm going to get rid of that, and then I have my psi plus and psi minus, these two diffracted waves, and we'll look at them all by themselves. And here's what they look like. Here, right next to the specimen, the colors are blue and yellow. This is completely imaginary amplitude, and there's no interference and no contrast. Why is there no contrast? Well, okay, so we were sitting here with the incident wave, which I say is amplitude 1, and then we're doing some perturbation in the imaginary direction. So imagine we just move this up and down slightly. That's not going to change the magnitude much at all. But then down here we have red and green. That means that the perturbation from the diffracted waves now is in the same direction as the real amplitude of the undiffracted wave, and so now the perturbation moves in this direction, and that changes the magnitude a bunch. So we get interference when we have moved down here a quarter of a wavelength compared to the original incident wave. Are you all okay with that? Yeah. Yes?
Why does the imaginary part contribute to the interference with the real part of that?
Well, you'll have to take my word for it. I can write down the equations, but the easiest thing is to say, okay, here we are. This is the incident wave has this amplitude. It's real value 1, and then we're adding to it these diffracted waves, which give a little imaginary component. And you can see that if I perturb this up and down a little bit, the magnitude, the length of the line I would draw from the origin out to there really doesn't change much at all. It changes in a quadratic term, and in this case it's something of the order of epsilon squared if epsilon is the size. Okay, but now if I'm in this regime where the perturbation is now along the real axis, then I have a perturbation that goes up and down like that, and so more obviously changes the magnitude. And so that's what's happening here. It's all imaginary. There's no perturbation there's no contrast. And then here, when the phase of the diffracted waves have changed, then we get contrast. Yeah.
I have a quick question.
Yeah.
So in this case, this is like the most simplest case, because then once you actually have like something that's able to interact with the wave, wouldn't you be able to push into those other regimes of colors, like the purplish and that tealish color?
Well, yeah, and I mean, if you look closely at this thing, so we start out blue and yellow, if you can believe, and then here we're sort of intermediate. So in that case, if we were to make a slice along here and look at, well, what's the variation, we would be moving maybe in this direction.
Oh, so we can still
Yeah.
do those transformations in the simplest case.
Yeah.
Okay.
Yeah. The two extremes. Okay, so now here's a trick. It turns out that no one focus. So I'm claiming that if we focus the objective lens below the specimen, we'll see contrast. Now here's a thought experiment. Suppose we focus the objective lens above the specimen. Well, I'll talk about this in a more concrete fashion later. But suppose we focus above the specimen. Well, the objective lens doesn't know that there's a specimen there, and as far as it knows, the wave fronts that it's seeing just came from infinity above, and so we can actually model what happens if we focus above the specimen by just extrapolating the waves back above the specimen and just say, okay, now when we focus above the specimen, we'll just see whatever waves would have been there in free space. And so if we look above the specimen, we do get contrast, and it varies, and it's 0 at the specimen. Okay, stranger than fiction. But I'll give you a more concrete way to look at that in a minute. But by convention, people give a defocus value, say I took my images at a defocus of 1 micron, and what that means is that the strength of the objective lens was turned down so that it's actually focusing 1 micron above the specimen. The other thing that we can do is we can say, okay, talk about a grating with periodicity d, and I'm going to say that this quantity spatial frequency is just the reciprocal of that. So a grating of 5 angstroms means I'm looking at a spatial frequency of 0.2 inverse angstroms. Now the phase shift is proportional to the amount of distance to this defocus quantity. And so we can write down the contrast transfer function using the quantities I've talked about before. We'll see that in a minute. Is this sine, it's a sine function, that's a sine function, minus pi lambda delta s squared. So you fix s, the grating periodicity, and as you vary the defocus, this gives you a sine function that is varying as you move above or below the specimen. Now, so this is what the contrast looks like as the amount of defocus. Okay, and I can keep saying defocus, the amount of defocus. But the other way we can look at it is we can say, well, what does the contrast look like as a function of the grating spacing of the spatial frequency? And that's what this is. So here what I'm doing is I'm plotting spatial frequency, and this is the amount of contrast we see. And if I pick a particular value of defocus, then this is what happens. At some spatial frequencies, I get positive contrast. At other spatial frequencies, I get negative contrast. And this so-called contrast transfer function is the sine function of this thing that people like to call chi, and that's this thing that I just told you about. So chi is a a parabolic function that's gradually increasing in the negative direction. And so you take the sine function of that and you get the contrast transfer. Yeah.
Then I had a question about the unfocused, because you showed that before, but then how come for the CTF we do not like show that wave portion?
Yeah. Okay. So this is a tricky thing. So here, this thing is a plot of that function as a function of delta, the defocus. And on the next screen, I'm going to show it as a function of S. Okay. So it's the, yeah. And, so this is it's just a sine function of the defocus, but it's a sine function of S squared. That's how we get this funny thing.
Back to the previous slide.
Yeah.
So if contrast is a function of the defocus as a whole, when collecting a data set at a range of defocus values, just looking at this graph, would if you were to collect a defocus value and then the opposite, would the combination of those two images or aggregates not turn to zero?
Oh, yeah. So you're saying, let's suppose let's collect data here and there. Okay. So the result is exactly the same, except the polarity is reversed. Okay. So white is black and black is white. So at this point, you could say, well, why bother focusing above the specimen? Let's focus below the specimen, and it looks like it's just as good. And we'll see in a few minutes why it's not just as good. But right now, it's kind of silly that we are doing that. Okay, so and then if we fix the defocus, then this is the contrast transfer as a function of spatial frequency, and this immediately tells you why people acquire images at different levels of defocus. Because as you change the amount of defocus, you squeeze and expand these oscillations. And the big problem here, of course, is that there is no contrast here, and no contrast there, and no contrast there, and that means you're not getting any information. So if you can squeeze and expand this function, you can in another exposure with another amount of defocus, you can retrieve information that was missing from the first one. Okay, so formally, if you want to see the math, so we say that we first unwrap the oscillations, and then this is what's left over, the diffractive terms, e to the I k zeta. Zeta is the difference in path length between a diffracted wave and undiffracted wave. And this is multiplying the original grating. And this k zeta is the same as the chi that I've been talking about before. And so, this is for you quantum mechanics folks. This is what's happening. Here is the undiffracted and diffracted wave, and intensity is just real part squared plus the imaginary part squared. And so if you go and you expand the square, you get this interesting bunch of terms. You get 1 plus 2 times sine of chi times the phase shift, plus another term that is of order epsilon squared, and the entire imaginary part is also a term of order epsilon squared. And I'm saying epsilon is small, so epsilon squared I'm just going to ignore. And so the main part of the contrast that we're seeing comes up from this term. So what do people do? Well, they ignore the constant background intensity, which is the 1 here. And for some reason, everyone throws away this 2 as well. And so people say that the contrast that relates the change in intensity to the change in electron phase is just this sine chi term, because that's the electron phase change, and we multiply it by sine of chi, and that turns us into the intensity change. So that's where this contrast comes from. Okay, cool. All right, so I was mentioning how many wavelengths we're talking about. I mean, 1 micron of defocus is a whole lot of wavelengths. It's 500,000 wavelengths away from the specimen. And when we're focusing that far away, then there are things that you have to worry about. So one is, in effect, here's the specimen, and here's where I'm focusing. And I'm basically taking an image of a diffraction pattern way up here. And now let's suppose that the electrons going through the optical system of the microscope are taking slightly different paths. So one comes in at an angle like this, another comes in an angle like that. Well, because I'm looking so far away from the specimen, that's going to make my diffraction pattern change its position depending on the angle at which the electrons come through. So it's very important that the electrons follow exactly the same path through the microscope. This is called spatial coherence in the microscope, and that's why we spend so much money. That's why we spend an extra $1 million to have a field effect electron source in the big microscopes, because that source acts like nearly a point source for electrons. So every electron takes almost exactly the same path through the microscope. And for the same reason, we have to have a small energy spread, because if different electrons came with different wavelengths, then you could imagine that that also would smear out that diffraction pattern. Okay, so I mentioned this issue of delocalization, and we can calculate how big the delocalization is going to be. So if I turn up the contrast on this image, you can see that there are fringes that go out quite a distance from the center of the image of my object, and we can calculate how far these images are going to be. So we just say that if we're looking up here, and there's the specimen, that this diffracted wave and this diffracted wave are going to be displaced according to the angle and the defocus distance. So if you go and if you calculate this distance r is delta lambda over d, and so if we put in some typical numbers, 1 micron, and we're interested in 3 angstrom resolution, so we say d is 3 angstroms, then this r is 200 angstroms. So that says that in this image taken with 3 micron defocus, and I want to have data out to 3 angstrom resolution, actually those fringes are going to be 200 angstroms away from the original object. So the people who did the trip V1 structure used boxes of this size, which were actually kind of tight, because what you really want is you really want to have 200 angstroms worth of space between the edge of the object and the edge of the box that you're using to make the images for reconstruction. Otherwise, if you crop this too small, then you lose some of those fringes, and that has the effect of reducing the amount of high resolution information that you actually pick up in your micrograph. Okay, and things get worse, of course, when people are trying to go to higher resolution, and things get worse when the defocus gets bigger. Okay, so that's the contrast transfer function to first order, and now we're going to go add the complications. Okay, so this is my diagram of electron microscope optical system. So here's the specimen. I'm just going to say we have a single objective lens, and this lens focuses the rays such that down here at the camera, I have reproduced the undiffracted and diffracted beams exactly, just magnified in scale. Now, if I defocus, what I do is I turn down the strength of the objective lens a little bit. And if I just follow the beams from the specimen, what happens is that this focus where the beams come together is now at the conjugate plane of the specimen way down there. And let's suppose that my camera is sitting up here. So this is a case where the camera is in effect looking above the specimen because I have reproduced this particular configuration of wavefronts here at the camera. Now, electron microscope lenses are not very good. They have a lot of aberrations, and the first one is called spherical aberration. And there's nothing spherical about the magnetic lens in an electron microscope, but this is the same kind of problem that comes if you have a glass lens that instead of parabolic curves, it has spherical curves. That is, a wavefront that goes at a high angle through the lens gets bent more strongly and comes to a focus closer than a low angle wavefront, which comes to a focus way down here. And this amount of change, you can say it's like a defocus change. This is a change in the focal length of the lens. And the change in the focal length of the lens follows something like this. There's a constant called CS, the spherical aberration coefficient, and that multiplies lambda squared, that is the wavelength, and S squared. And so the real CTF now has this perturbed amount of defocus, or if we go put in all of the term, if we go and expand it all, it looks like this. So we have, as we increase the defocus, we have these negative sine function, but then we have this positive extra term on the sine function that's going in the opposite direction. And so CS is like 2 millimeters, so that's a whole lot of angstroms. That's 20,000 angstroms. Spherical aberration becomes important only when S is above a certain value and S is more than about 4 angstrom resolution. Then there's another phenomenon that happens, which is your specimen has stuff in it that has atoms, and the atoms have nuclei, and even though these atoms are fairly light atoms, an electron can come by very close to the nucleus and get scattered by a big angle. And we have something called an objective aperture, which captures the electrons scattered at very high angles, and so those electrons are lost. And that means then that when there is stuff in the specimen, actually the amount of the intensity that winds up at the camera is reduced a little bit. And so this is we call amplitude contrast. So if I combine everything that I've just talked about, then we have the defocus term, we have the spherical aberration term, and then we have a little amplitude term. This amplitude is like 5 or 10% of the size of the defocus contrast. Yeah.
I have a silly question. So like, what if you're like studying a protein that like can generate radicals using electrons? Would that interfere with your like, I guess, amplitude overall? Because
oh, okay. So so suppose you have something that that generates radicals due to the irradiation by electrons. Yeah, and this is happening all the time. This is called radiation damage.
yeah.
Okay, so here comes my high energy electron, and it hits a carbon-carbon bond, and it doesn't do the elastic scattering thing where it just gets a phase shift, but it actually transfers some energy to the electrons in that carbon-carbon bond and breaks the bond. And so now you have these carbons with unsatisfied valences, or you break a water molecule apart. And so So you're producing then charged species and so on. So a simpler issue. Let's suppose that we're looking at a protein and it has a lysine residue in it, so it has a positive charge that is sitting there more or less permanently. Okay, so that's going to scatter the incident electron a little bit more than just having the nuclear positive charge, but it has the net positive charge even. What it has is a incompletely shielded nucleus on that nitrogen. Yeah, and so you get a little bit more phase shift from that. Yeah, and so some people have tried to recognize, okay, what is the charge on this atom from analysis of very high resolution EM data, and in principle you can do that. You have to be a little careful because you're busy making charges as you cause radiation damage. But anyway, that's a very interesting thing to think about. Yeah. Okay, another question. Yeah. Yeah, okay, so heavy atoms, of course, are going to give you more of that high angle scattering, so they give you more of this amplitude contrast. And no one deals with this quantitatively that I know of, but in principle you could. Because a high amplitude contrast looks like in a conventional image just the same as a high defocus contrast. But if you looked at, if you have then data taken at a series of defocus values, in principle, you could unscramble that and see, oh, okay, we got more amplitude contrast from this part of the protein. Yeah. It would be like anomalous data. Yeah. Yeah. I haven't heard of anyone doing that, but it's worth thinking about. And now that everything seems to be possible with real high resolution, you can start to do things like that. Yeah. Okay, so this is what I talked about before. This is the contrast transfer function where I just have the defocus term, but now when I add these other terms, then several things happen. So one is, notice that the chi function as a function of spatial frequency was just a parabola, but now it's turned into something more complicated. And that's because the CS effect, the spherical aberration effect, changes that curve and flattens it out. And what happens is that the oscillations slow down and then they actually reverse in polarity. And then if I were to continue this, they would start oscillating faster and faster as the CS term kicked in. The other thing is that there is this little bit of amplitude contrast here. So before that started out at 0, now it starts out with this little bit of amplitude contrast. So this is why everyone focuses above the specimen, is the following. The amplitude contrast is negative. So if we can also make the defocus contrast negative in this region, in this low frequency region, then the amplitude contrast and the defocus contrast add together, and that lets us see the outlines of our proteins more easily. And if we were focusing below the specimen, then then the contrast transfer function would start off here, cross through 0, and then start oscillating upward. Okay? Yes?
The contrast then negative and positive contrast are good, or would you rather have like taking the function?
Yeah, in principle, negative and positive contrast would be just fine. It's just a matter of, does your protein look black or white in your micrographs? But the processing programs can handle that, you just tell them my defocus is the opposite polarity. Yeah. Okay, so yeah, so here's the explanation. This is why everyone uses underfocus. Now, if you weren't doing image processing to remove the contrast transfer function oscillations, the best you can do is to do a very small amount of defocus, which then gives you this pretty much always negative contrast over a pretty big range of spatial frequencies. And this is what people in material science do all the time. This is called the Schertzer defocus. And so it gives you a pretty good looking image. The only problem is that the amount of signal you get at the low spatial frequencies is really small. So we don't like it. We'd rather process our images and get rid of the contrast transfer function. Finally, I wanted to talk about phase plates. What does a phase plate do? So a phase plate is a device that's put in the so-called diffraction plane of the objective lens. So if we have a parallel beam of incident electron waves, then they come down to they get focused down to a point. And the diffracted waves get focused down to points, but those points are displaced from the center. So if we then put an object here in the center that changes the phase just of the electrons passing through that little area, we can do tricks to make contrast. So here what I've done is I've sort of changed the real valued wave function, the red here, into an imaginary valued wave function by doing a 90-degree phase shift in the phase plate. And so now here we have the imaginary valued diffracted waves interfering with the imaginary valued undiffracted wave, and that gives us contrast all the time. What it does is it changes the CTF so that instead of being a sine function, it's a cosine function, and if we have zero defocus, then chi is 0, and so we have contrast of 1 all the time. And this is wonderful because this saves us from the loss of information that is gotten in using defocus contrast. So you get actually twice as much signal using a phase plate than you get using defocus contrast. So it's a wonderful thing. So a practical phase plate was invented by Rado Danev, and this is a plot of, this is minus the CTF. This is a plot of the contrast transfer function as a function of defocus. This dashed line is 0 defocus, and you can see that here it is perfectly flat from 0 spatial frequency up to here about 4 angstrom resolution, and then it starts oscillating. And why do you think it starts oscillating? Why is it oscillating at the highest resolutions? Remember, this is now cosine of chi, and chi has the defocus term and it has the spherical aberration term, and the spherical aberration term starts taking off, I said around 4 angstrom. So what we're seeing is the oscillation starting up from the spherical aberration. But this is glorious, and this is what an image looks like. You can actually see your protein, whereas this is the usual defocus contrast where you can see the high resolution details of the protein, but there's not a lot of low frequency signal. So phase plate is a wonderful thing. Rado's phase plate, you probably even have his phase plate in some of your microscopes. it's great because it gives you all this signal. This is pretty nice for tomography, but it turns out to be really no big deal for a single particle, and that's because the high resolution information actually gets degraded by his faceplate, because the faceplate is actually some physical stuff. It's a thin carbon film, and so it introduces noise at high spatial frequencies. Okay. The contrast transfer function is actually a two-dimensional function. So if I were to plot it in 2D, here's what it would look like. And if I just take the section along this orange line, that is what I would see, right? The 1D function I was talking about before. But the contrast transfer function depends on both the spatial frequency in the x direction and the spatial frequency in the y direction. And if you have astigmatism, if something is distorting, or if you have a small distortion in the objective lens, or some other charging or something that's going on that distorts the image, you can get astigmatism. And if you look in one direction, the contrast transfer looks like that, and in another direction, the contrast transfer looks like that. And so astigmatism is a big deal when it comes time to process the images. But if you get the estimate of the amount of astigmatism right, there's no problem. Now, this is the contrast transfer function, and this is the square of the contrast transfer function. So why do we square it? Well, you'll see in a minute, but if I do the square of the contrast transfer function, then what happens is that I get a high intensity 1 here at a peak here, and then at 0 when the contrast transfer function crosses 0, and so on. So this is now the square of the contrast transfer function. And this is something that you will see when you're running the microscope. The microscope computer often gives you this display of the power spectrum of an image. And the power spectrum of the image has these black rings, which are called tone rings, and these black rings are at the zeros of the contrast transfer function. And depending on the amount of defocus, you see these rings either spaced out or compressed. And if you look and see out to what resolution, you can see these rings that tells you up to what resolution you're getting a signal. Now, when I give you this two-dimensional representation of the CTF, or in this case of the power spectrum, what I'm actually doing is I'm giving you the amount of intensity at various spatial frequencies, so that every point in this plot corresponds to a grading direction and spacing. So for example, if I start to move and look at points at various horizontal directions here, I see that these correspond to gratings in particular directions and spacings, and the farther I move out, the finer the gratings are. And we'll see in a minute that if I have then all possible grading spacings and directions, I can reconstruct images. Okay, so we've seen this. There's interference. The lens does things to perturb or change the contrast transfer function, and phase plates are wonderful. Okay. Now, I'm now going to tell you why gratings are all I need. First, I'll do it in one dimension and then in two dimensions. So, Joseph Fourier in the 19th century was a mathematician who showed that if you give me a function, the function can be reconstructed by adding together sinusoidal functions. So here I've added together, what is it, six 6 cosine waves of various frequencies, and once I've added them together, I get this white curve, which is indistinguishable from the original function that I had. So I would say that, well, these 6 terms, these are at different spatial frequencies. I'll use u here as the spatial frequency variable. But then you probably want to ask me, well, where did I get these magic numbers, which are the numbers which are the amount I scaled each of those cosine waves to make it fit to make a perfect fit to the Gaussian function that I started with? And the answer is I just asked the computer to do it. So I can say compute the values of some function, and I'll call this g of x, a function of x, and I put it through this algorithm, the Fourier transform, and out comes a function of u, and then what I used as those amplitudes is just points plucked off of that curve. And that shows me then how to reconstruct the original information. And so that then says that you give me a function, and we pass it through the Fourier transform, out comes another function, and this contains the same information. I can reconstruct the original one perfectly, or nearly perfectly, with this entirely different kind of information. Now, this is the one case where the shape of the function going in and coming out looks the same, a Gaussian function, and that's sort of the only case. Well, in other cases, if you have a lattice, but I'm not going to talk about. So the Fourier transform is this thing that says I get the Fourier transform of this function g of x by multiplying it by a complex exponential, which is the thing that mixes the two variables u and x, and I integrate it so that there's no x left, and then I just have this g of u. Now, here's another case. I'm going to try to reproduce this rectangular function, rect of x. And so I add in a bunch of terms, and I add in more and more terms, and here I am adding in 10 terms, and I get nowhere near convergence. So this is one of the this is a function that the Fourier transform has a really hard time with. That is the reconstruction of a square-shaped function, one with a discontinuous jump. And if I look at what happens when I calculate the Fourier transform, I get this horrible-looking oscillating thing that oscillates off to infinity. It's called a sinc function, and this is one of the sort of pathological functions that's not reconstructed very well in the Fourier transform. So if you look up in a book, you can look at tables of Fourier transforms, and this is what you would see. Gaussian goes to Gaussian, the rect function goes to this something called a sinc function. Now, Fourier transforms have a bunch of interesting properties. Linearity, you add together two functions and you get you can add together the Fourier transforms. There's this interesting scale property where if you squeeze in one domain, you expand in the other domain. And I'll show you the shift function in a minute, and then I'll show you convolution. Convolution is the kind of thing that a microscope does in imaging something if the microscope has a finite point spread function. So let's suppose that we have this sort of one-dimensional object that has this, this kind of intensity distribution. And let's suppose we have a microscope that has a point spread function that looks like that. So what we get out of the microscope is the original object that went in that is smoothed by this point spread function h. So h, we'll call it the kernel, and h is 0 everywhere except in the vicinity of 0 argument. And so what happens is that we take the original function, we look at it in the neighborhood of x, weighted by h of s, and add those up, and that gives us the output. So, for example, if I take this edge here, and I use h, which will then smear together or add together values in the vicinity of that edge, you'll see that the edge then becomes smoother. Okay, so this is that's a convolution operation. Okay. All right, so let's move on to 2 dimensions, which is more interest to us in doing microscopy. So we can do the same kind of trick, but in this case, instead of showing you cosine functions, I'm showing you gratings. And so this is a representation of the Fourier transform. And as I move around in this plane, I'm describing various kinds of gratings. So, so as I add in more and more terms, I'm adding in more and more gratings. And as I fill in the plane here with all of the possible gratings, turns out that if I go out that far, I get a pretty good reconstruction of my original function. So this is a 2-dimensional Gaussian. Now, if we do something kind of like the rect function, this is now something that is 1 in the middle of in a disk in the center and 0 outside. Then as we start adding together the various grading terms, we start to get something that kind of looks like a disk, but you can see that it has ripples. And so what we're doing is we're getting something that's kind of looked a lot like the incomplete Fourier representation of the rect function, again because we have sharp edges. Now I'm going to talk about the shift property, and we're going to go from real numbers to complex numbers. So up till now, I've been showing you Fourier transforms of functions that are symmetric around the origin. And now I'm going to start making them no longer symmetric around the origin. So here's my circ function, and now this is just showing real numbers. It starts out red, green, red, green, red, green, which means we're just seeing values along the real axis. But if I start moving it off center, you can see that I get all these other colors, and that's because with the shift of A and B, what happens is that I'm multiplying the original Fourier transform by an extra term, which is a complex exponential. And as I move in different directions, I get these ripples in different directions, and the farther out I go, the finer the ripples are. So far I've shown you these Fourier transform pairs. The circ function turns into this oscillatory Bessel function, and what I've shown you is the shift property. But now I want to talk about convolution. So convolution in 2D is again one of these integrals where we have the original image, and it's weighted by values of this kernel, so we get the smooth output from that operation. And it's expensive to compute. So if I have 1,000,000 pixels in my image, then in principle what I have to do is I have to compute 1,000,000 output pixels, and I have to so I take the 1,000,000 input pixels, and in principle I have 1,000,000 pixels in the kernel, and so I have a million computations to do. Turns out that there is a wonderful algorithm called the fast Fourier transform that much faster. So if I need to do a convolution of an image with 1,000,000 pixels, I can do it with the FFT in about 10 million operations. It's amazing. So anyway, so this is the way that I would most like to do a convolution. I take my object, I compute its Fourier transform, I take my kernel and I compute its Fourier transform, and then I multiply the two, and then I do an inverse Fourier transform, and that is the result. So this is exactly the same result as if I took that and I did that convolution integral on it, and I would get that. Okay. So the trick here is that convolution in Fourier space is just a multiplication. I just multiply the g times h in Fourier space, and that does the convolution. So that's one of the most useful things that you can do with Fourier transforms. Yeah, question?
Is there a function then to then sharpen that after you do that? Because I guess it's a little bit distorted after you've done that. But
yeah.
You showed that earlier with
Yeah.
the other shapes.
Well, so think about that. So if I were to multiply by something that looks like 1 over h, okay, in principle, then I would undo this blurring,
Okay.
And in fact, that's, there's the sharpening of a map that you do in structural biology. And so what happens is that you have a 3-dimensional map, and you have a blurring due to all of the processes like the microscopy and interpolation and everything going on. So then you can undo at least partially that by going and dividing by the inverse kernel.
Okay.
And so you can sharpen it. Now, it doesn't work perfectly if you literally multiplied it by 1 over h, you would then have infinite magnification of any defects in the signal, and won't work. Won't work. Yeah. Okay, so now here's how we use the contrast transfer function. So let's suppose we took some random object. Okay, so literally some random noise, like looking at a carbon film or amorphous carbon film. So we can take its Fourier transform, and we get this colorful thing because in general it's complex numbers. Okay, we multiply it by the CTF, which is all just real numbers, green, red, right? We multiply them together and we get the product, which looks like that. And so this is what the image would look like. And if you've worked with an old-fashioned electron microscope where you can just turn the knob and see, this is kind of thing that you would see in a carbon film imaged in an electron microscope. And the more you defocus, the more kind of coarse this pattern is, you see. Now, when you're sitting at the microscope, you actually get a display that looks like this. This is the magnitude squared of the Fourier transform. That's the power spectrum. And the power spectrum is the thing that I showed you before. It sort of shows you what is the magnitude of the various Fourier components that the image contains. And so again, you see these tone rings. So that's the Fourier transform. No one displays that. They display this, which is just the same, just colors are removed, basically. Yeah?
So the microscope is doing all this for us as we're
Yes. So at least when people ran the microscope themselves, they would turn on the so-called FFT display, FFT for fast Fourier transform, and it would show this display being refreshed every fraction of a second.
If that's the case, I understand how the microscope or both operators are to get the point spread function, the Fourier transform of that would be the CTF, But the object, though, how does the microscope know what the object is? The microscope just seeing, like.
That's right. So the microscope sees this. And what I'm showing you is how I would simulate an image. Or conceptually, what is happening if we knew exactly what the object looked like. But it turns out that almost any object that you would put in the microscope, you get a pattern that looks like this. It doesn't matter very much what the actual specimen contains, because everything is multiplied by the CTF, so you keep seeing these zeros coming from the CTF. Okay, so the next step I want to do is, let's see, where are we? Okay. I want to talk about two more nice properties of Fourier transforms. One is the rotation property, and one is the so-called Fourier slice theorem. So the rotation property, so if you like this math, you can see that this integral is the same as this integral, but here I've represented u and x as vectors, and you can see that this complex exponential just contains a dot product of u and x. So that says that if I rotate this function, it will result in the rotation of that function. And so here's an example. Can you see that? Yeah, just barely. So the Fourier transform rotates in the same way as the original object. So this is how CAT scans work. So this is a cross section of your body showing something, I guess your liver or something, and you're in the CAT scan machine. X-rays, a sheet of X-rays are being generated and passed through your body, and a linear array of detectors are picking up whatever X-rays came out the other side, a projection of the density of that slice of your body. So there's this wonderful theorem that says, well, in principle, this two-dimensional density has a Fourier transform, and if we compute a projection, that projection has exactly the same values as the 2D Fourier transform just evaluated along this line, okay? And that's because if we evaluate the Fourier transform with the v variable being 0, then that drops out of the complex exponential. And so we can say, this is the projection, and then this is a 1D Fourier transform of the projection. So here's how it works. So the CAT scan machine computes a projection in this direction, and then it rotates the X-ray source in the detector and takes a projection in this direction and that direction. And then we make use of the idea that as you take projections in different directions, then that gives us Fourier transforms along different slices as we get the data from different angles. Okay, so here's a fancy example. So here's an object. We compute a 1D projection. We take the Fourier transform of that projection, and then we insert it as a slice in a two-dimensional field. And then as we take projections in various directions, we fill in different slices. So here we've filled in half of the slices, and you can see that we've kind of done a so-so reconstruction of the original object. It's anisotropic. There's higher resolution in this direction than in that direction. But if then I fill in the entire Fourier plane, I get a pretty good reconstruction of the original thing. So use these 1D projections to fill in the two-dimensional thing. And you can do the same thing in 3D. So on a computer, of course, the FFT that the computer does, it's discrete and is really basically the same thing. It's a complex exponential. The only difference is you're dividing by the size of the two-dimensional array. And so for any object, the computer will give you a discrete Fourier transform. Now, you would probably say, well, no, there's something wrong here because here is a 32 by 32 pixel image, and here is a 32 by 32 pixel Fourier transform, but each pixel has a real and an imaginary value. And so there's something wrong here as far as the information. And it turns out that no, there is no extra information here because the real part is symmetric and the imaginary part is anti-symmetric in this thing. So the fact that we put this in colors is pretty, but is maybe misleading because there isn't twice as much information there. Okay, so now your microscope is acquiring an image, and in the image processing, the Fourier transform of the image is being operated on. And what is the resolution? What is the highest spatial frequency that is preserved in this process? Well, let's suppose that this is an n by n image. The highest spatial frequency, which is basically this amount of this distance, is n, that is the number of pixels in one dimension, times the pixel size in Fourier space. So what that means is that the highest available frequency is the frequency that you would get if you had a grating that was exactly twice the original pixel size. So, for example, if I have 1.5 angstrom pixels, then the highest available frequency is going to be 3 angstroms. This is the so-called Nyquist limiter, Nyquist frequency. And you can kind of imagine that. If I'm going to make a grating, the finest grating I can make that is going to be valid is going to be alternating, 1 minus 1, 1 minus 1. And so that's the very finest grating I can make. Okay, so there's a 3D Fourier transform, and the computer can compute that too, and it has a bunch of properties, and the properties are all the same. That is, there's convolution, rotation, and projection all work. And so that's how we can do 3D reconstruction. So let's suppose that we have a macromolecule and it has some kind of 3D Fourier transform. Then the slice theorem says that if I take a projection of this, its Fourier transform in 2D is a slice of the 3D. And so then I can make use of the rotation property again and collect 2D images gotten at different projection angles, and then build up the 3D Fourier transform. And it's the same trick where, because we get rid of one term in the complex exponential, it's like taking the projection and then doing a 2D transform on it. That's how you prove the slice. So we can make use of the rotation property and fill in the whole Fourier space. And that's how we can do 3D reconstruction. Yeah?
How does it work for version from frequency domain to, time domain to frequency domain? So here you just to listen to the frequency domain, right? Is it the same thing as the signal processing, right?
Right. So there are two ways to do this reconstruction. So the way I like to think about it is this, because I like Fourier transforms. But if you don't like Fourier transforms, you can do something called back projection. So what you do is you imagine you have these 2D images, and and you have a slide projector in a smoke-filled room. And so you project one of those 2D projections through the room in one direction, and then slide projector from another direction and from another direction. And you get a sort of blurred out reconstruction of the 3D object. And then you can do what's called filtered back projection, where you do these back projections and then you just operate it on it with a particular kind of filter that reweights the Fourier components, and you get a reconstruction. So there are basically three methods. There's the Fourier slice method. There's the filtered back projection method, which I think is how a lot of CAT scans work. And then there is so-called algebraic reconstruction. Algebraic reconstruction sort of represents the back projection process as a big matrix. So you take your images as vectors and you multiply it by this huge matrix, and out comes a three-dimensional result.
Linear algebra.
It's linear algebra, yeah. And this is a linear process, yeah. Yeah.
How do we get the angular information from this property?
That's the trick. And we will talk about that in the next lecture in a few minutes. Yeah. How do you get the angular information? And as you can see, getting the angles right is going to be really important. Yeah. Okay, so that is the end of this first lecture, and I'm only 10 minutes behind schedule. Yeah.
Can I have just a few? This is for teaching purposes
Yeah.
that I had earlier. Sorry, this is back way earlier.
Yeah.
So, if the vacuum in theory, right, the electron coming down to be the speed of light, right? So then why it's not, right? Why it's not only 2/3 or something, right? But did you, I guess, multiply by the relativistic term, right? To get so that should be the same as to get the original speed of light back, right?
Well, so
Column from the Fourier column.
yeah. So the electron is coming down at 70% of the speed of light, passes through the specimen. The specimen, because of electrostatic potentials in the specimen, is going to shift the phase of that electron wave a little bit.
So this is after it hit the specimen, not before. After it hit.
Yeah, so after it hits the specimen, then there's a little bit of phase shift of the electron waves, and then it hits the camera still at that 70% of the speed of light, and the camera then detects the intensity there.
But if it's close to vacuum, would that be the same speed of light before it hit the sample?
What about vacuum?
If it's the vacuum, right, theoretically,
Yeah.
it should be at the speed of light and all very close to the speed of light before it hits the sample.
Yeah, so of course the vacuum is very good because you don't want the beam to be interacting with gas molecules in the vacuum system. So yeah, so this is it's moving at the same the electron is moving at the same velocity everywhere. Maybe its velocity went up and down a little bit in the specimen, and that's how the phase got shifted. But it's still at the same velocity as it hits the detector. And we're just looking at the intensity, the number of electrons per second that wind up at the detector.
I guess that was my last question. So remember you just showed a diffraction, and then what happened? Like I thought it was multiple wavelength of 2D psi theta, not just and you said D psi theta. I didn't see the two because it actually length this distance has to travel, right?
Mhm.
Right law, right? It's
Yeah.
way
Mhm.
psi theta, but I saw the end. So what happened to the actual distance that travel for diffraction?
Okay, so we're thinking about one electron is passing through the microscope. But after it passes through the specimen, the wave function has been changed a little bit. And we can describe the change of the wave function as to say there's the original incident wave. Now we're talking about electron waves. One electron produces waves, right? And then two more diffracted waves come off that are going at slightly different angles. And so according to this simple approximation to the complex exponential that we call the, oh my goodness, I'm blanking on the thin specimen approximation. We can just say that what's happening is we now have these three waves, the original and these two diffracted waves, and they interfere, and that gives us contrast.
But they would travel same distance to make up the, right, to catch up with the original phase shift, right? Yeah.
Well, no, so the diffracted waves are moving at a different angle, okay? But the velocity is the same. This is an elastic scattering event. And so these diffracted waves have a slightly different path length, but same velocity, yeah. Yes?
You mentioned that three ways of reconstruction.
Yeah.
Is there a way, like, which like option is the best?
Yeah, so the three ways to do reconstruction, which option is the best? There are things that you can do in algebraic reconstruction that are nice, like you can control what happens when information is missing. So people doing electron tomography where there is a big missing wedge in Fourier space, you can tweak the algebraic reconstruction to handle that in the way that you want. Whereas the Fourier slice theorem is faster, but that assumes that you have equal coverage in the entire Fourier space. Yeah. Oh, yeah.
Could you collect the backscattered electron
Mm-hmm.
and show information on the thicknesses?
Right. So could you collect backscattered electrons and get information? It turns out that there's a lot less information there than in the forwardly scattered electrons, so no one bothers doing that. If you want to know what elements there are in your sample, then you can look at the inelastic scattered electrons. That is where energy is transferred from the incident electron to the specimen. And there are two ways to do that. One is you look at the spectrum of energy loss, which is going to be different depending on what atoms the beam is traveling through. The other thing is you can look at X-rays emitted from the specimen by the same process. So people in material science do that all the time. We don't. To distinguish oxygen from carbon and nitrogen the signals are very weak. Okay, time for, do we get a coffee break? I need